A billion-dollar telescope lost its steering and then kept aiming anyway. In 2013, after 2 reaction wheels failed, Kepler couldn't point precisely, but data kept arriving. How does a blind telescope keep finding planets? Everyone called it over. 2 of 4 reaction wheels had failed. 3 are required for full control. All commands paused. The mission faced a game over screen. So what could spark an impossible comeback in nights of silence? Internal gyros, reaction wheels, let Kepler pivot by spinning. But in 2012, one failed, and by May 2013, another was gone. Just 2 left. Physics says you need 3 for stable pointing. So how did stars stay still on Kepler's detector? Thrusters could steady Kepler, but the price was enormous, burning through precious fuel in months. The mission demanded years of stable sight. Could another hidden force be waiting to swap in for a missing wheel? But sunlight kept causing trouble. Its radiation pressure, barely thicker than a breath, shoved Kepler off balance. The very act of orbiting the sun threatened to end the mission. What if this troublemaker could switch sides mid-story? Then came a wild thought. What if solar pressure was tamed? If Kepler pointed along the ecliptic, sunlight might push evenly, balancing around its center of mass. Could the enemy force actually become a missing reaction wheel? It almost worked. Almost. Sunlight and 2 wheels steadied most axes, but the roll still drifted. Periodic thruster nudges could fix this, but would the jiggle blur precious exoplanet signals? Not quite locked down. Not yet. So 2 reaction wheels control side to side and up down. The sun pins the roll, and minute thruster corrections trim away any lingering drift. Just enough force, just enough fuel. Could this keep Kepler steady for years? Kepler's goal: detect brightness dips as tiny as 100 parts per million, planetary shadows smaller than a raindrop on a lake. One twitch, one unsteady moment, and the signal vanishes. Could this rescue plan ever be that precise? NASA ran on-sky tests, the 2-wheel concept demo, and against all odds, the data whispered yes. Ecliptic alignment with microthruster trims brought science-grade stability back. Could this broken telescope go planet hunting one more time? NASA approved a radical new blueprint, the K2 mission. Kepler would scan new fields along the ecliptic, jumping every 70 to 80 days. The telescope wasn't dead, it just needed a new flight plan. Almost every protocol changed. K2 only observed fields near the ecliptic, scheduled momentum dumps, tuned cadence, and recalibrated its photometer. Even how Kepler's team sliced the sky and measured starlight was reinvented from scratch. Here's the twist. The very sunlight that once threatened to ruin the mission became a stabilizing force. Kepler's engineers made solar radiation pressure act like a third virtual reaction wheel, enabling precision that once seemed impossible. Did it work? K2 observed for 4 more years, confirming over 500 new exoplanets and opening up studies of young clusters and strange worlds. Kepler and K2 together redefined the modern catalog of planetary science. Charlie Sobek and the Kepler team didn't just save a project, they wrote the K2 playbook for future missions in trouble. Campaign after campaign, Kepler scanned the ecliptic until the tank ran dry. By November 2018, Kepler and K2 finally fell silent, their fuel spent. But the methods invented to rescue a failing telescope now echo across exoplanet science, its precision data still reshaping what we know about distant worlds. Engineers now use solar pressure and micro-actuators to steer CubeSats, sailcraft, and even extend satellite lifetimes. If you can fly a broken telescope with sunlight, what else can you pilot using the free forces in space? Kepler's K2 mission used 2 wheels, ecliptic pointing, sunlight's pressure, and precise thruster trims to rescue its vision, turning disaster into a discovery engine. You now understand something most science textbooks leave out. Hit subscribe. The next discovery is already waiting.